So that was the crust. Next thing down is the mantle. The internal structure of the mantle is basically the upper mantle, a transition zone, and the lower mantle. Or sometimes the transition zone gets lumped in with the upper mantle as the bottom of it. But generally speaking, the upper mantle is from the base of the crust down to 400 kilometers, where it changes into transition zone. Transition zone from 400 to 670 kilometers, at which point there's an abrupt jump in velocity as we go into the lower mantle. Lower mantle goes all the way from that 670 down to the bottom of the mantle, approximately 2,900 kilometers. More, precisely the 2,885 kilometers. In the ocean area, there is another low velocity zone at 100 to 200 kilometers. But that's different than the transition zone. So you can see that here, that low velocity zone that we see in the ocean is this dark band up here where the mouse is. Then down here is the transition zone from 400 to 670 kilometers. Then the lower mantle. And so this from about 40 down to about 2,900 is the mantle. The mantle is solid, except, this is the exception because, geology is full of exceptions or partial exceptions. In that low velocity zone, largely under the ocean crust, but sometimes showing up under continental crust, is a zone of partial melting. Definitely not complete melting, otherwise our S waves would stop there and it would be really distinctive. But partial melting. So there's some solid and some liquid and some mush, semi-solid, slushy type stuff. And so it slows down the seismic waves. Doesn't stop them, but it slows them down. So it's a low velocity zone. The mantle as a whole behaves plastically, even the solid parts. It's very slow convection. Something that we can see to help us grasp the idea of solids that can flow are glaciers, made of solid ice, but they flow, they move a couple meters a year. The mantle is much slower, but it's the same idea. There's so much pressure, and in the case of the mantle, so much heat as well, that solid rock can bend and flow and move. Mantle plumes are areas that are exceptionally hot. They're hotter than the average mantle. They're balanced out by cooler than average areas. Therefore, it averages out to the average temperature of the mantle for any given depth. There are about 100 known hotspots around the world. These hotspots sometimes punch through all the way through the crust to create volcanoes and island chains like Hawaii. And sometimes they don't actually manage to punch through and make islands, but we have ways of detecting them. The easiest is, of course, a volcano. These hotspot volcanoes are very distinctive, especially once we've figured out where the plate boundaries are. And then we have this volcano chain out in the middle of nowhere, seemingly. So we've looked at the crust, we've looked at the mantle, now we'll look at the core. The core is about 3,500 kilometers in diameter. It's big. It's roughly the size of our moon. So our core is about the same size as our whole moon. Now, not a space station, an actual moon. The core has two parts, although there's some new research that's suggesting a third part, but classically we're absolutely sure about two parts, and so that's what we're going to focus on. We have an inner core and an outer core, and these are defined by S and P waves. Just like I was showing earlier in the lecture today, the S waves cannot penetrate liquid, and that's how we know the outer core is liquid. And there's convection in that liquid outer core. That convection is how we get Earth's magnetic field. Ultra vital. The only reason you're alive is because the outer core is liquid. So that rock, thousands of miles below the surface, that's not really rock because, first of all, it's liquid, and second of all, it's almost purely nickel and iron with some sulfur and a few other things slightly mixed in. So this giant, thick layer of molten metal, thousands of kilometers below the surface of the Earth, is why you're alive. Without that magnetic field, the surface of the Earth would be bombarded with cosmic radiation, and we'd all be dead. We never would have even been born. So the convection in that outer core is super important and pretty cool. Now, let's look at defining the layers based on rheology. This is looking at how they're responding to stress, how they flow, how they move. The lithosphere responds to stress by bending, flexing, or breaking. It's a rigid layer. It's composed of the crust and the very top of the upper mantle. So only a tiny bit of mantle, but all of the crust is part of the lithosphere. The asthenosphere responds to stress by flowing. It's the plastic part of the mantle. So it's all the rest. The rest of the upper mantle and all of the lower mantle and that transition zone. So the lithosphere is much thinner than the asthenosphere. The boundary between the two is a thermal boundary. Since it changes from lithosphere to asthenosphere in that upper mantle, we know it's not a composition change, otherwise we'd call it, upper and middle mantle. We don't. We call it all upper mantle. It's all the same material. But it gets to a certain temperature and it's no longer brittle. It's like if you have plastic at room temperature and it's rigid and you start heating it up, like say you've got some Tupperware or Rubbermaid and you have your food sitting in it and it's nice and rigid, it's holding your food just nice, and you put it in the microwave too long and you get it out and your dish is all floppy and you might spill your food, who knows. But it gets more and more flowy and plasticky and bendy as it gets hot. So does the rock. A temperature boundary is called a geotherm. It's where that temperature is reached all across an area. It's sort of like a topographic map, except instead of elevation surface, it's a temperature surface. And the geotherm that we care about for changing from lithosphere to asthenosphere is the surface where the rock is 1,280 degrees Celsius. Much hotter than anything you've probably ever experienced. Some torches can get that hot. Your oven can't. Your fireplace can't. Your campfire cannot. Your gas stove cannot. It's really hot. Not hot enough to melt that rock, but definitely hot enough to make it much more bendy and flowy and start behaving plastically instead of brittly. So here's a side-by-side look at the seismic layering on the left and the rheologic layering on the right. We can see crust, continental crust being about 40 kilometers thick. Oceanic crust is there, but it's so thin that it's just part of that line at about 6 kilometers thick. And then at the bottom of that is the moho, the Mohorovičić discontinuity. Then we have upper mantle, transition zone, and lower mantle. Those are seismically defined. Then we have outer core and inner core. Over here on the right, if we look at rheology, we have lithosphere, which is much thicker than that crust because it includes crust and the top part of the mantle. And it's rigid. Below it, it is thicker under the continents than it is under the ocean. But even the ocean lithosphere is thicker than continental crust. That's kind of an important detail to just remember in the back of your mind. Below it is asthenosphere. So all the rest of the upper mantle, all of the transition zone, all of the lower mantle, lumped together as the asthenosphere. So if we look rheologically, we have fewer layers to worry about. Makes it kind of tempting to say, hey, you know what, I'm just going to use this. But the seismic layers are important as well. And the names are much more familiar. Outer core and inner core instead of liquid solid. But the terms lithosphere and asthenosphere are definitely common terms that you hear in geology or dealing with a geologist. So let's look at a cross-section. Near the top, we've got some crust, we've got the moho, and we have the part of the mantle that's in the lithosphere. So this is the thickness of the continental lithosphere, about 150 kilometers. And here's the thickness of the oceanic lithosphere, about 100 kilometers. And below it is the asthenosphere. Notice at the mid-ocean ridge, the asthenosphere is reaching right up there. It's almost to the surface. And actually, at the dead center of that mid-ocean ridge, you have asthenosphere spilling out. It's the magma. That's how we're actually creating new crust. Asthenosphere comes up and hardens, and as they move away and let some more up, it hardens, and it's growing new crust. Now, a term that's kind of important in geology is isostasy. Kind of fun-sounding word. You can imagine somebody getting drunk and walking around saying, isostasy, isostasy, isostasy. But more important than how fun it sounds is what it means. This is what lets things float. For example, if you take a block of wood that floats in water, it's going to float the same every time unless you change your water into like salt water or into magma or some other fluid. As long as you float that block in regular water, it floats the same every time because of isostasy. What it says is you have that mass of wood, and as it goes into the water, it's displacing that water. It's moving water from where it wants to be. When the amount of water moved weighs exactly the same as the block of wood, it's going to float right there. That's Archimedes' law of buoyancy. It'll only sink until the water that it displaces has an equal mass to the mass of that wood. Now it works for things besides wood and water. This is how we can have a ship float on the water. A big, massive, huge ship made of steel can float on water because it has lots of space inside. It's not solid steel. Therefore, it can displace a lot of water, enough to equal the mass of that boat, and it floats. It also works with rock. We can have rock sitting on top of the crust, trying to sink down into the mantle, which is more mushy, but it'll only sink so much until it displaces enough mantle rock to support its weight. Now, if we have a rigid layer on top, or at least semi-rigid, and we put a load on it, it'll squish stuff under that layer. It's like if we had a piece of cellophane or a piece of cardboard across the top of the water, and we set something heavy there. It'll bend that rigid thing, it'll displace water, and it'll float. But it changes how it floats, and it, very importantly, flexes that thing that we had on top of the water. This happens on Earth. When we have an ice age, we have glaciers that come out across the crust. Huge, thick, mile-thick glaciers. That's a lot of ice. That's heavy. It flexes the crust. Just like this little cube is flexing this crust in this picture. We remove it, and it slowly goes back to normal. But pretty darn slow because we're dealing with rock. On the other hand, if you don't have a rigid surface and your block is too dense, it's like if you have a boat but you put too much stuff in it, so there's too much mass, it'll just sink right in and it'll keep going down. So isostasy, you can have different thicknesses, like different blocks of wood. This one in the center, it's sticking way far down, but it's also sticking further up. The blocks of the wood on the side are smaller, so they don't stick as far down, and they don't stick as far up. This kind of gives you an image of a mountain chain. We have coastal platform, or continental platform rather, and then the crust is only so thick. Then we go to the mountain chain, and they have deep roots because of isostasy. The only way to have a high mountain is to have a deep root, because the crust and the mantle have different densities. Now, far below the crust is a point where everywhere along that line there's the same pressure. So the pressure under the mountains, the pressure under the plains of North Dakota, if at a certain depth, the pressure is all the same. It's called the level of compensation. It works with wood blocks and water. It works with crust and mantle. It works with anything where you have isostasy. So we can see here, instead of blocks of wood and water, we see crust, continental crust, ocean crust, lithospheric mantle, asthenosphere, and down here somewhere in the asthenosphere is the level of compensation, where the pressure is all the same. And it's because the mass of everything in this column A equals the mass of everything in column B. Asthenosphere is denser, but then water is less dense. Basalt is denser than continental crust, but the continental crust is higher. So it all averages out, and right here, the mass from this point all the way up to the top of the line, and the mass from here all the way up to the top of this line is identical. So the pressure is the same.